AI is everywhere.
AI.
Artificial intelligence.
AI.
It drives our cars, cleans our houses, some people use it as therapy. Even the algorithm that recommended you this video is a neural network. Over the past decade, we've experienced the biggest AI revolution in history, fueling what many experts already call the fifth industrial revolution. Yet, one of their founding fathers died thinking they were of no use, and we almost abandoned them. In this video, we will travel through history, from the earliest AI models to the algorithm that powers the entire AI industry. My goal is to make each explanation as intuitive as possible. And for that, we have to travel back in time. It was the 1950s. World War II was over, the economy was growing, and the Cold War wasn't at its peak. At that time, many scientists and engineers were working on Alan Turing's biggest invention, the digital computer. What had begun as a powerful machine for code-breaking Nazi communications was now becoming a tool for exploring all sorts of things. From calculating missile trajectories and running simulations, to even playing simple games. Everyone seemed to love computers. But they had a problem. For any given task, you had to design an entire machine just to solve it. And remember, we're talking the 1950s. Computers then filled entire rooms. You can imagine the effort required to solve even a simple task. And this is where a 29-year-old psychologist named Frank Rosenblatt entered the story. See, Rosenblatt wasn't trying to solve this problem per se. What he wanted to do is to have a better understanding of how the brain works. Back in 1943, two researchers, Warren McCulloch and Walter Pitts, were trying to copy how the human brain functions. And for that, they studied neurons. A biological neuron has dendrites, which are thin branches that collect electrical signals from other neurons. Those signals travel to the cell body, and if they are strong enough, the neuron fires, sending a pulse to the next neuron. Otherwise, it stays silent. What they did is introduce a digital model inspired by a neuron. This model takes inputs through its dendrites, each carrying a numeric value. These values get multiplied each by a different number called a weight, and the results get added together. If the total is bigger than a certain threshold, then the neuron fires, returning a 1. Otherwise, it stays silent, outputting a 0. Rosenblatt loved this concept, but it had the same problem as before. Once you built a neuron, it was fixed. You had to set the weights by hand for every single one, and that meant creating an entire custom computer. But Rosenblatt had an idea. Instead of manually setting every weight, what if the machine could adjust them by itself? Let's try a simple problem to illustrate how this works. We want to tell if a point lies above or below a certain line. If it's above the line, our neurons should output a 1, and a 0 otherwise. Starting from the basic McCulloch-Pitts neuron, Rosenblatt added two new parameters, a bias and a learning rate. You'll understand why in just a second. Let's feed the neuron this point right here, which is obviously above the line. Like before, we multiply each input by its weight and add them together. Then Rosenblatt introduces the bias as well, which, just like the weights, is random at first. Finally, we check if the result is bigger than the threshold. It is, so the neuron outputs a 1. That means we got the correct answer, so we leave the weights unchanged. Now let's fit it a point that is below the line. This time our expected result is 0. We repeat the same process, but the neuron gives us a 1, which is wrong. So now we can learn from our mistake. The way Rosenblatt taught the neuron how to learn was with these two simple rules. For the weights we add the learning rate, multiplied by the input value, and an error metric. And the bias is the same, but without any input. To obtain this error metric, we calculate the difference between the expected output and the one the neuron predicted. This basically tells us whether the neuron has overshoot or undershoot. By applying these learning rules across many training examples, the neuron slowly improves. At first, it will get most of the points wrong, but with each update, it sets itself closer to the right decision boundary, until eventually converges onto the optimal weights, which in our case are -1.2 and 1.3. From that point on, the problem is solved, and the neuron won't get any problems wrong anymore. By combining multiple of these neurons with sensors and some thresholds, in 1957, Frank Rosenblatt had built what was, in essence, the first trainable AI model in history, the Mark I Perceptron. This machine could learn to recognize different shapes and patterns with almost no human intervention. For the late 1950s, this was revolutionary. The excitement was so great that the New York Times ran the headline, "New Navy device learns by doing." The Navy revealed the embryo that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. And it wasn't just the New York Times. Rosenblatt himself fueled the excitement. Stories about the creation of machines having human qualities have long been a fascinating province in the realm of science fiction. Yet we are about to witness the birth of such a machine. After this achievement, many expected the Perceptron to be a machine that could learn to solve almost any problem, and the spark of revolution in computing. Rosenblatt received significant funding from the US government, and the stakes were really high. But that optimism wouldn't last long, because in 1969, Marvin Minsky and Seymour Papert published a book called Perceptrons. In it, they exposed a critical weakness that would prove almost fatal to Rosenblatt's model. Let's return to our toy problem. Suppose we change the task slightly. Instead of classifying points above or below a line, we want to tell which points are inside or outside a circle. What Minsky and Papert proved is that for a perceptron, this is impossible. The perceptron cannot solve problems that are not linearly separable. Or, in other words, problem where no single straight line can divide the classes. This shifted the perceptron's reputation, from a machine that could solve any problem to a model that could only handle a small fraction of them. Seriously, try to come up with a useful problem that's linearly separable. There are not a lot of them. After Perceptrons was published, research funding, including support from the US government, quickly dried up. For almost 15 years, neural network research largely stalled in what we now call the first AI winter. And tragically, in 1971, at the young age of 43, Frank Rosenblatt lost his life in a boating accident, unaware that his invention would one day ignite a revolution, but just 50 years later. What Minsky and Papert didn't know is that the very problem they described in their book had already been solved 4 years before. Meet Alexey Ivakhnenko, an Ukrainian researcher who, in 1965, published this book, that I'm not going to say the name for obvious reasons. He built on Rosenblatt's idea, stacking neurons into multiple connected layers. Then, in his 1971 paper, Polynomial Theory of Complex Systems, he created what is basically the earliest deep neural network ever published. Let's get down to it. Once we understand the perceptron, MLPs are pretty straightforward. As I said, instead of just one neuron, we stack many of them in layers. Each neuron passes its output forward, feeding into every neuron of the next layer. This is where that iconic neural network diagram we've all seen comes from. To solve the non-linearity problem, after computing the weighted sum, each neuron applies a non-linear activation function. Today, the most common choice is the rectified linear unit, or ReLU. But in principle, almost any non-linear function works. Now, Ivakhnenko didn't use this exact architecture I'm describing. We're focusing on a more modern shape of the multi-layer perceptron, but his idea was quite similar. Adding these activation functions comes at a cost, though. With a simple perceptron, we could train it using Rosenblatt's original learning rules. But because of the multiple layers and nonlinear functions, that method no longer works. So we don't have an efficient way to train this model. In his original paper, Alexey Ivakhnenko introduced a technique called the group method of data handling. But because interest in neural networks was low at the time, and since he was working in the Soviet Union, his ideas were largely unnoticed. It wasn't until the mid-1980s that David Rumelhart, Geoffrey Hinton, and Ronald Williams finally made popular the holy grail of machine learning: backpropagation. Backpropagation is, without a doubt, one of the most important algorithms in the history of computing, and it is the cornerstone upon which all modern AI systems are trained. Let's go back to our toy problem. We still want to classify which points fall inside the circle. This time we'll use a very simple MLP. It has 3 layers: an input layer, an output layer, and a hidden layer. In the output layer we have 2 neurons. If the first one outputs a higher value than the second one, we predict that the point is inside the circle. And if the second is higher, we predict the opposite. So for a point that is inside the circle, the expected output is 1,0 and 0,1 if it's outside. As with the perceptron, we initialize all of the weights and biases randomly. The only real difference is that we now have more weights and biases, but nothing more. Let's walk through a single forward pass with one data point. Each input is sent to the next layer, where we compute the weighted sum, just like with the perceptron. And then we apply the activation function, which in our case is just ReLU, so nothing happens. We do this for each neuron on this layer, and the process repeats for the next layer, passing the results forward. In the output layer, instead of ReLU, we use a different activation function, called softmax, which just turns our outputs into probabilities that end up adding to 1. That way we can tweak the network more accurately. It is important to know that if we modify the weights, the output changes dramatically. So we cannot just tweak them by hand. That's why we need a way to train the network. The first step is the same idea Rosenblatt had with his perceptron. We need a way to measure how wrong our predictions are. This measurement is what we now call a loss function. One of the simplest and most common choices is the squared error loss. To compute it, we take the difference between the network's output and the expected value, square that difference so that negative errors don't cancel out, and finally sum up all of those squared differences. Now, if you think about it, a neural network is nothing more than a mathematical function that for any given input produces a loss as an output. So we can imagine collapsing the entire network into a single expression, f theta of x and y equals L, where x is our input, y is the expected value or ground truth, and L is the associated loss. Our goal is to make this error as close to 0 as possible for any given input, because if we get loss 0, it means that we got the right answer. Back in 1967, Shun Ichiamari proposed doing this with a method called stochastic gradient descent. Let's simplify things with a basic function f of x. This function represents our loss function, so we want to find the value of x that minimizes this loss. Imagine starting at some random point. This represents our random weights and biases. We want to move them to that minimum. Now, I've chosen to show you the line that represents our loss function for more clarity. But with most neural networks, this function is so complex that we can draw or visualize it in any way. Still, even if we don't know the whole shape of the function, we can calculate its slope, or in math terms, its derivative. This derivative is negative if we are sloping downhill, and if we move forward, it will gradually get closer to 0. After that, it turns positive when we go uphill. If we want to move closer to the lowest point of the function, we first introduce a new parameter called a learning rate, just like with the perceptron. With it, we can apply a simple update rule. Starting from this current value of x, we subtract the derivative, scaled by this learning rate, which controls the size of each step. It is essential that we subtract this derivative, as if we didn't, we would go up and not down. In effect, this expression moves us downhill towards smaller function values, and repeating this process gradually brings us closer to the minimum. But notice how crucial the learning rate is. If we go back to the starting point and increase it too much, we don't smoothly fall into the optimal minimum. Instead, the steps overshoot, pushing us away and leading us to converge to a less optimal solution. Likewise, if we take a smaller learning rate, we do converge to the optimal point, but the steps become so small that it takes forever to do so. Thus, the importance of setting an accurate learning rate value. The thing that makes training neural networks hard is that calculating this slope or derivative is not as straightforward as in this simple example. Instead of updating a single point, we update all of the weights in the network. And instead of a single derivative, we need the gradient. This gradient is all of the partial derivatives of the loss with respect to every weight. If that sounds confusing, don't worry, it will all make sense in just a second. Remember, no matter how complex it is to calculate, this gradient is nothing more than our slope. And backpropagation is the algorithm that efficiently computes this gradient, allowing us to train the network. This is the expression that we'll use to calculate the gradient.
Huh?
I know. It looks scary, but give me a second and you'll see that this is not that complex. Let's make things simpler by removing all of the colors. That way we will get a better understanding of what's going on. First, we'll number the layers of the network from 0 to 2. Then, within each layer, we'll number the neurons starting from 0. So, if I say layer 2, neuron 0, you know that I'm talking about this neuron right here. Now, look at the formula. These blue L's represent the layers, and these red I's and J's are the neuron indices. Now, let's split this expression into 3 parts. We'll start with the first term. This tells us what we want to compute. It is the partial derivative of the loss function with respect to a single weight. Let's zoom in into just one of the weights. In this term, W is that weight we're calculating. We know that L is the layer, I is the neuron in that layer, so neuron 1, and J is the neuron in the previous layer, so neuron 0. Remember, in our earlier simple example, we asked, how should we move our point to make the function smaller? Here is the same idea, except now the question is, how should we change this specific weight to reduce the loss of the whole network? Now let's skip ahead to the last term in the expression. This one is the easiest one. It is just the output of the previous neuron. In this case, neuron 0 in layer 1. We computed it in the forward pass, so it's just a matter of storing it and looking it up now. Finally, the middle term. This is the crucial term, and it gives backpropagation its name. There is something vital to notice here. There's no reference to the previous layer or any other neurons, just this neuron 1 in layer 2. Why is this so important? Because this exact same term shows up for every weight going into that neuron. So if we calculate it once, we can reuse it for multiple weights. Now let's expand this expression a bit further. At a first glance, it looks even scarier, but it really isn't. This middle term breaks down into the derivative of the squared error. And that's just the difference between the output of that neuron and the expected output, which is one straightforward operation. And the right term is just the derivative of the activation function. What about that mysterious C factor? We still don't know it yet. Well, we actually do know what it is. It's just the weighted sum we already computed during the forward pass. And that's it. That's how we calculate the middle term. Now, this term is so important that it gets its own special name, delta. Let's refactor the original formula to use this delta term. See, each neuron has its own delta. We don't know most of them yet, but once we do know them, updating the weights become just one multiplication. And for the biases, this delta term is already the update factor. Now that we know how to get the deltas for the output neurons, what about the neurons in the next layer? Well, this time it's even easier. To get the delta in neuron 0 layer 1, we can just take the sum of all of the deltas from the layer on the right, which is the one we already calculated, each multiplied by the weight that connects them with the current neuron. And all of that multiplied by the derivative of the activation function. It's like the weighted sum we did on the forward pass, but inverted. The rest is the exact same as before. And that's backpropagation in detail. I've skipped some parts for simplicity, but the algorithm itself stays unchanged. It's called backpropagation because the deltas are calculated at the output neurons, and then propagated back through the network layer by layer. It's a neat trick that saves us from doing a huge amount of redundant computation. This was huge. It threw the non-linearity problem out of the window. Suddenly, neural networks could tackle tasks that once seemed impossible. Think I'm exaggerating? Well, listen to this. No, this is not a computer having a stroke. This is NetTalk, a neural network developed by Terry Sejnowski that learned to turn written English into speech sounds in 1987. And this...
There's just one thing I can't stand in my family. My baby, my stomach knows I can't even get to sleep for a minute. He won't stop jumping around in the bathtub. In the bathtub? No. In the crib. He eats the...
It's the same model after being trained with just 10,000 words. To put it into perspective, in '87, Sonic the Hedgehog wasn't even around, and Mario Brothers was just 4 years old. Yet we sort of had AIs already talking. And NetTalk wasn't alone. Dean Pomerleau created ALVINN, a neural network designed for autonomous driving, in 1989, beating Elon Musk's effort by more than 20 years. And many other researchers were building neural networks for all sorts of things. Naturally, for his contributions, Geoffrey Hinton was awarded the Nobel Prize in Physics in 2024, together with John Hopfield. But wait, if neural networks were invented so long ago, why didn't we have widespread neural networks until just a few years? Well, back in the 80s and 90s, computers looked like this. Not very powerful looking, if you ask me. The big problem with neural networks is that to solve complex problems, you need a large, complex network and enormous amounts of training computation. This meant that neural networks, while exciting in theory, were mostly useless in practice. And just like that, once again, funding was cut, attention shifted elsewhere, and the hype surrounding neural networks died off. And this marked the start of what we often call the second AI winter. From the early 90s into the 2000s, progress on neural networks slowed to a crawl. But in 2012, a young researcher named Alexey Ivakhnenko revived an idea first introduced in 1989 by a machine learning legend, Yann LeCun, and used it to win one of the toughest AI competitions in the world. That single breakthrough was the spark that ignited the modern deep learning revolution, a revolution that would forever transform not only AI, but science, industry, and even the way we live our daily lives. But we'll cover that in part 2 of this video. If you like this content, please like and subscribe. It's just me making these videos, and they take a lot of time to make, so any support is much appreciated. With that being said, I'll see you guys in the next video. Bye bye!